So we need to find the equation for V average. So here is alpha, and it's a sine wave, and we stopped at pi because of the freewheeling diode, and then we started again at pi plus alpha, and we stopped at 2 pi, and this is the wave. So as you can see, we can do the average over pi because this is repeated. So V out average equal to 1 over pi integration from alpha to pi V max sine theta d theta equal V max over pi multiplied by 1 plus cos alpha. Compare this to the fully controlled. So for the fully controlled, we were integrating from alpha to pi plus alpha, which give us V out average equal to V max over pi cos alpha plus cos alpha, which is 2 V max over pi cos alpha. So as you can see, for the semi-controlled, you are controlling the start, but you have no control over the end because the end will be always at pi. Why? Because once the voltage start to reverse, the freewheeling diode will conduct. But for the fully controlled, you are controlling the start and you are controlling the end. So the end is function of alpha and the start is function of alpha. And if you look at the equation here you have one which is constant cos alpha, and this one from cos 180. And here you have the start and the end cos alpha and cos alpha. So the fully controlled, you can control the average using alpha, which can give you a negative or positive voltage. But for the semi-controlled, V average is always positive. Okay, so for alpha equal 0, you are getting V max over pi. For alpha equal 90, you are getting V max 2 V max over pi for alpha equal 0. For alpha equal 90, you are getting V max over pi. For alpha equal 180, you are getting 0. So this V average is variable from 0 to 2 V max over pi. This is for alpha equal 180, and this is for alpha equal 0. So V average is always positive. But here, if you have alpha equal negative or positive 180, you get negative 2 V max over pi. If you have alpha equal 0, you get positive 2 V max over pi. And if you have alpha equal 90, you get 2 V max. Sorry, you get 0 because cos 90 is 0. So your voltage is controlled from negative to positive for the fully controlled. So this is a comparison between the fully controlled and the semi-controlled. So we can get I out average for the semi-controlled. It's a V out average negative E divided by R equal to V max over pi 1 plus cos alpha minus E over R. And I out average is I out RMS because we have a highly inductive load. Also, we can get V out RMS. So this is a waveform from alpha to pi. So V out RMS will be square root for 1 over pi integration from alpha to pi V max square sine square theta d theta equal to square root 1 divided by 2 pi integration from alpha to pi 1 minus cos 2 theta d theta equal to V max square root pi minus alpha plus sine 2 alpha over 2. So you can see here that the RMS is also controlled, not like the RMS for the fully controlled, which was Vmax over root 2, and it was uncontrolled. So to summarize, we had the single phase full wave uncontrolled, and we had the single phase full wave fully controlled, and we have the single phase fully controlled, semi-controlled. So single phase full wave semi-controlled, and this is how we sketch the semi-controlled. Just we add a diode here to indicate it's a semi-controlled. So for the full wave uncontrolled, V average is 2 Vmax over pi. V average is 2 Vmax over pi cos alpha. V average is Vmax over pi 1 plus cos alpha. So these are the three full wave rectifiers we studied. So we studied the full bridge, which has 4 diodes. And we studied the fully controlled, which has 4 thyristors. And then we studied the semi-controlled, which has 2 thyristors, 2 diodes, and a freewheeling diode. And this is a summary for what we studied so far in the full wave rectifiers. Okay, so today we will continue our power electronics chapter. So what we covered so far, we finished rectifiers, and to study rectifiers we studied diodes and thyristors, and we studied the uncontrolled, the controlled, and the semi-controlled rectifiers. And before moving to the next part, we will stop here and we will go to chapter 6. And chapter 6 is DC motors speed control. How we can do speed control for DC motors. And then we will continue the DC to DC converters, and then we will go again to DC motors speed control. So for DC motor speed control, we will do this using rectifiers, and we will do this using DC to DC converters. So instead of finishing chapter 5 and then moving to chapter 6, we will do them together. So chapter 6, DC motors speed control, and we will discuss the DC machine speed control using the using rectifiers. But we need to understand or highlight some important basics before moving to DC motor speed control. So if you have a motor and this motor is coupled to a mechanical load, so you have a motor driving a mechanical load. So the motor will output a torque, let's name it as T motor, and the load itself will have a reaction or T load, okay? If the load has no reaction, has no torque, you don't need a motor to drive it, okay? So it's logical to assume that there is torque coming from the load. And we have a speed here, omega, and as you can see that the speed in the same direction of T motor, because the motor is the acting torque, okay? So this is called motoring. You are doing motoring. So if the speed is in the same direction of T motor, we are doing what is called motoring. So the mechanical equation we have here is T motor minus T load equal to J omega dot, and omega dot is the acceleration we have. And this is the mechanical equation, and J is the inertia of the motor and the load together. So if we sketch the torque speed characteristic, and if we say here we have the speed and here we have the torque, so if the torque and the speed are positive, we call this forward motoring, okay? And we call this quadrant 1. So quadrant 1 is a forward motoring quadrant. So FM means forward motoring. Or we can take the same exact layout, but we can reverse all of them. So we can reverse remove this, and we can remove this and this, and we can reverse all of them, okay? So we will say that T motor is going up, and the speed of the motor is going up, and T load is in opposite direction. So we reversed all of them. So you are still doing motoring, but you are doing motoring in the opposite direction. So if we sketch the torque speed characteristic here, is speed torque. So we are here. So the torque is negative and the speed is negative. So assuming this direction is the positive direction, so this direction will be the negative direction. And we are doing what is called reverse motoring, or quadrant 3. So in quadrant 3, you are motoring. Why motoring? Because the torque of the motor and the speed are in same direction. So we are motoring. And we are motoring in the reverse direction. So this is the third quadrant. Now let's take this one again. Now if your speed is forward, but in this case your speed is forward but your torque is reverse, so here we are not doing motoring, we are doing braking. Why we are doing braking? Because the torque and the speed of the motor are in opposite directions. So if we sketch the torque speed characteristics, speed torque, so the speed is still positive but the torque is negative. So here we reverse the torque, so the torque is negative and the speed is still positive. So what we are doing here, we are doing forward because the speed is still positive, but we are doing braking. So we are doing forward braking. This forward braking can be regenerative, or this forward braking can be just braking. So to brake the motor or to stop the motor, you need to take the energy from the mechanical system. And you can take the energy from the mechanical system and lose it in friction, like when you use the brake in your car. Or you can have batteries in your car, and when you brake, you convert the car into a generator and you take the inertia or the kinetic energy and convert it to electric energy and store it in the batteries, like hybrid cars. So braking doesn't mean you are regenerating energy. You will be regenerating energy if you have a regenerative braking. Okay, so if you have diesel cars and you are braking, this is friction braking. But if you have a hybrid car and you are braking, it can do friction braking or regenerative braking and stores the energy back in the batteries. And the last case is this reverse motoring case. But in this case again, we will reverse the torque coming from the motor. So in this case, if we look at the speed torque characteristics, we will be here. So the torque is still positive, but the speed is negative, and we are doing reverse braking, and this is our quadrant 4. So these are the different operation for the motor. The motor can be forward motoring, for braking, reverse motoring, reverse braking. And if you can do all of these, you have a 4-quadrant operation. So if you think about your car, and you can move your car forward, and you can brake it forward, now you have the first 2 quadrant. So you have forward motoring and you have forward braking. If in your car you can only drive forward and you cannot stop it, you have only the forward motoring case, which is not logical, but some applications you need just to drive it forward and control the speed, okay? And if you are able to move your car forward and stop it forward, so you can do braking, and you can move it reverse and you can stop it on the reverse, so you can brake it, you will have the 4-quadrant operation: forward motoring, forward braking, reverse motoring, reverse braking. Okay, so there is different options for the drive. So we call this the motor drive. So the motor drive can be a 1-quadrant motor drive, or the motor drive can be 2-quadrant. And for 2-quadrant, it can be the forward 2-quadrant or the reverse 2-quadrant. This is reverse braking, reverse motoring. So the motor drive here is 2-quadrant, the motor drive here is 1-quadrant, and the motor drive here is 4-quadrant. So 2 quadrants means you can accelerate it in one direction and brake it in the same direction. 1 quadrant means you can accelerate it on this direction only, you can change the speed, but you cannot brake it, you don't have a way to stop it. The 4-quadrant means you can move it forward, brake it forward, move it backward, and brake it backward. And based on our knowledge of DC machines, we know that the omega is proportional to the voltage and the torque is proportional to current. So we can add here, this is voltage, current, voltage, current, voltage, current, and so on. So to have a motor drive that can give us the forward motoring, we need to be able to inject a positive voltage and positive current. To have a drive that can give us the reverse motoring, we need to be able to have a negative voltage and negative current. So here the voltage is negative and the current is negative, and so on. So the ability of the drive depends on the polarity you can generate from your voltage and your current.